Hello friends, in this video I am going to explain you the topic Karlin-Rubin theorem. So before discussing the topic Karlin-Rubin theorem, we first discuss about Neyman-Pearson fundamental lemma. In NP fundamental lemma, we we find the most powerful test between simple null hypothesis versus simple alternative hypothesis. But in Karlin-Rubin theorem, we uh, we applied that we find a uniformly most powerful test between between composite hypothesis, simple null hypothesis, and composite alternative hypothesis. So what's the difference between most powerful test and uniformly most powerful test? So most powerful test applies when the testing is between simple null hypothesis and simple alternative hypothesis. But in uniformly most powerful test, the testing applies between simple null hypothesis and composite alternative hypothesis. So in in NP lemma, we we know the two condition, which is E naught of phi of x is equal to alpha, and phi of x is equal to 1 gamma and 0 under the condition which is given which is given in the PPT. Karlin-Rubin theorem is useful when we dealing with uniformly most powerful test. It provides condition under which a test is based on monotone likelihood ratio, which is the best possible test among all others of the same size. So now what is monotone likelihood ratio? So monotone likelihood ratio is the term when in a statistic it is increasing or it is decreasing. That's the monotone likelihood ratio. In hypothesis testing, we often want the best test to decide between null hypothesis and alternative hypothesis. The Neyman-Pearson fundamental lemma gives the most powerful test, and however, Karlin-Rubin theorem extends the idea to cases where H0 and H1 are composite hypotheses. And KRT applies only to one-way hypothesis and not for two-sided test or non-parametric test directly. So now we are going to prove Karlin-Rubin theorem. So let theta be a real parameter of density under consideration, and let x be a random variable having PDF f of x comma theta with MLR in T of x. In first part, for testing hypothesis h theta less than equal to theta naught against hypothesis k theta greater than theta naught, there exists a uniformly most powerful alpha level test given by phi of x is equal to 1 gamma and 0 under condition t of x is greater than equal to and less than c. The constant c and gamma are determined such that E naught of phi of x is equal to alpha. So consider the hypothesis h dash theta equal to theta naught against k dash theta equal to theta 1, which h dash and k dash are simple hypotheses where theta 1 is greater than theta naught. So theta 1 is greater than theta naught is the condition of monotone likelihood ratio. Now by NP fundamental lemma, the most powerful test is given by phi of x is equal to 1 gamma and 0 under condition p1 of x upon p0 of x is greater than equal to and less than k. But we have that the family of density has MLR property in T of x. Therefore, the condition that P1x upon P0x greater than k can be replaced by Tx greater than c. Therefore we change the phi x term P1 of x upon P0 of x changes to T of x greater than c equal to and less than c. Now the above most powerful test is independent of theta 1. Therefore, above is MP test for all the theta greater than theta naught. Thus, the test is given by condition 3 and 4 is uniformly most powerful alpha level test. Now, second part, the power function beta of theta is equal to E of theta, where phi of x of the test phi of x is strictly increasing for all point of theta for which 0 less than beta of theta less than 1. Now let us consider theta dash less than theta double dash be another pair of parameter points For testing hypothesis h double dash theta equal to theta dash against hypothesis k double dash theta equal to theta double dash where theta double dash greater than theta dash. So now similarly by NP lemma, the most powerful test is given by phi of x is equal to 1 gamma and 0 under condition t of x greater than equal to and less than c. Now as we know theta double dash is greater than theta dash, so power function of the test is beta of theta double dash is equal to E1 of phi of x is equal to 1 minus beta, which is the power of the test, and beta of theta equal to E naught of phi of x is equal to alpha, which is the size of the test. So by corollary of NP lemma, we know that size is less than power. Therefore, beta of theta dash is less than beta of theta double dash provided theta dash is less than theta double dash. And beta of theta is equal to E theta phi of x is increasing for every theta for which beta of theta is less than 1. So now we make the power curve where as the theta increase, the beta of theta is also increasing. So the curve will look like this. Now the third part, for all theta star, the test determined by part A and B is uniformly most powerful for testing hypothesis H star theta less than equal to theta star against K star theta greater than theta star at level alpha star equal to beta of theta star equal to E naught of phi of x. So now the test given by condition 3 and 4 maximizes power theta 1. It is found that the test is independent of theta 1, hence it maximizes power for every theta greater than theta star. The test becomes uniformly most powerful for every theta greater than theta star. Now to show that the same test is the alpha level test. So now we consider arbitrary points, say theta star less than equal theta dash less than equal to theta star. Now since the power curve is increasing, we have power function of theta dash less than equal to power function of theta star. That is b of theta star less than equal to b of theta b of theta dash less than equal to b of theta star. But beta of theta star is equal to E naught of phi of x is equal to alpha star. So therefore we get b of theta dash is less than equal to alpha star. Now since theta dash is an arbitrary chosen parametric value under hypothesis H star, the equation is true for every theta less than equal to theta star. Now beta of theta less than equal to alpha star for every theta less than equal to theta star, and E naught of phi of x less than equal to alpha star. So as both conditions occur, thus phi is the alpha level test. So the test given by condition A and B maximizes power at all theta greater than theta star. Again, it satisfies the size condition. Hence, it is the alpha star level test. Therefore, the test is uniformly most powerful alpha star level test for testing H star theta less than equal to theta star against hypothesis K at level alpha star. Now the fourth part, where theta is less than theta naught, the test minimizes beta of theta as theta is less than theta naught among all the tests satisfying B. So here we consider the same hypothesis H dash against K dash where theta 1 greater than theta naught. And by NP lemma, we get the phi of x value under different conditions. So the proof of this part is from the fact that the test which minimizes the power for testing a simple hypothesis against a simple alternative hypothesis is obtained by applying the NP lemma with all inequalities reversed. That is, so that is suppose phi of x is equal to 1 p1 of x upon p naught of x greater than k. So we will write it as p naught x upon p1 of x greater than 1 upon k, which is equal to k dash. And similarly, we will write for gamma and for 0. So now it is given that the family of density has MLR property in T of x as it is given, and here theta 1 less than theta naught. Therefore, P1 of x upon P naught of x is monotonically increasing, but by MLR property, the condition that P1 of x upon P naught of x greater than 1 upon k can be replaced by T of x greater than c. Therefore, we get phi of x is equal to 1 under 1 gamma and 0. So this test is identical to the test given in the theorem. Therefore, the test is the uniformly most powerful test. Again, we have chosen arbitrary theta 1. Therefore, we can take any other point less than theta naught, that is theta less than theta naught. Then the test which is uniformly most powerful minimizes beta of theta for all theta less than theta naught among all the tests satisfying condition B.